Cool. Can everyone hear me okay in the back? Awesome. All right. Hi, everyone. Thanks for coming to my talk today. I'm going to talk about my work on verifying indistinguishability of privacy-preserving protocols. This is joint work with my advisor, Gowtham Kaki, and our collaborator, Wustrow, and we're all out of CU Boulder. Privacy today is critical, whether it's to protect sensitive information like healthcare data, to preserve internet access in the face of censorship, or even to protect physical safety in the case of journalists and dissidents. The protocols we're going to be talking about today aim to provide these kinds of critical protections. Specifically, they'll look to provide privacy properties like herd anonymity, where an individual cannot be distinguished from other members of the herd, confidentiality, and N-1 privacy. These protocols that we're going to talk about today are also going to be communication protocols, where participants are going to be communicating over a network. Importantly, because participants are communicating over a network, we're going to be talking about these privacy properties with respect to an attacker on that network, specifically an adversary in between these participants. I mentioned a few privacy properties in the previous slide, but really we're going to be talking about one in particular. We can boil all these properties down to indistinguishability. And essentially what we're asking here is, can an attacker distinguish between two pieces of information or two participants? For example, we might ask a simple question like, can an attacker distinguish between these two encrypted messages, hello Alice or hello Bob? Now, of course, what we want from our protocols is that an attacker cannot distinguish between those. Unfortunately, what we've seen in practice is that there are a variety of flaws in the protocols that we use today that unfortunately violate these kinds of guarantees. So given that these flaws exist today, it's clear that simply relying on expert review and testing is not going to be sufficient to ensure that these properties are protected moving forward. So I'm going to advocate for also using formal verification here. And I'm going to be talking about one approach to formally verifying these kinds of properties for these protocols. Specifically, I'm going to cover three different challenges as well as our contributions in this talk, and you can find some more information in the paper. First, current models of cryptography are either too difficult to automate or too imprecise, and so we're going to propose a balanced approach. Secondly, reasoning about non-determinism is hard, so we're going to extend some prior ideas to get rid of concurrency, and we'll talk about that a little bit later. Finally, we're going to take a look at TLS-ECH as a case study. TLS-ECH is a protocol that aims to hide which sites users are connecting to. It has been formally verified under a prior model, but as we'll see, the prior model that was used to verify this protocol excludes some trivial leaks. We're going to talk about how we helped verify TLS-ECH and also some fixes that were required to the model in order to verify the privacy properties we're looking for. I'm going to start off by talking about the different models of cryptography. Specifically, the gold standard model for how we model cryptography whenever we want to verify protocols is in this computational model. In this model, messages are going to be bit strings, and properties as well as cryptographic primitives are going to be probabilistic and computational. So for example, we might ask something like we might want to verify a property like the below property, where we might want to ask, can an attacker distinguish between two pieces of information, A and B, with non-negligible probability? In other words, we want it to be the case that an attacker can distinguish between two pieces of information with negligible probability, meaning less than epsilon. However, we don't care about attacks that are going to take an infinite time to run. We only care about practical attacks. So we're going to restrict this to an active attacker that has polynomial time and some bounded number of queries. Now, as you can see, this model is very precise and realistic because it reflects some of the actual constraints we're dealing with in practical properties. Unfortunately, like a gold, it ends up being cumbersome to actually use. This is partly because it requires cryptographic expertise to frame the privacy properties you want in this model. And furthermore, because we're trying to verify such precise properties, they end up requiring more manual effort. Notably, this is the reason why, though the computational model is the gold standard, it's typically only used to verify cryptographic primitives, not actually protocols that use those primitives. Instead, most protocols are verified in a different model called the symbolic model. This is a simplified abstract model of cryptography where messages are no longer going to be bit strings, they're going to be abstract terms instead. We're now going to model attackers' capabilities using equational theories that end up looking something kind of like this in practice, where you can say, If an attacker knows an encrypted message, and they know the key that was used to encrypt that message, then the attacker can derive the original unencrypted message. Notably, in this model, cryptographic primitives are going to be ideal. So we're essentially assuming here that they leak no information without the key. We're not reasoning about partial leakage, typically. The benefit of the symbolic model is that it's much easier to automate these proofs, especially using equational reasoning. Unfortunately, it ends up being imprecise, and this is a real issue whenever it comes to privacy properties. For example, let's consider the original question I posed. Can an attacker distinguish between these two encrypted messages? If we were to ask this question in the symbolic model, we would have to conclude, no, we're using ideal encryption, the attacker doesn't have the key, so there's no way we can distinguish between them. In reality, these messages are going to have different lengths. So that means that the encrypted versions of the messages are likely also going to have different lengths. An attacker doesn't need the key to distinguish between them. It simply needs to check the lengths of the messages. The problem that we have here is that the symbolic model is not precise enough for verifying these kinds of indistinguishability properties. And since we're boiling all the privacy properties we want to verify down to indistinguishability, this means that we could end up verifying protocols in the symbolic model that have trivial attacks against them. It's these kind of attacks that we aim to address. So our approach aims to balance some precision and automation. Like in the computational model, we're going to reason about messages as bit strings. Similarly, we're also going to reason to some extent about probabilities, but we're going to adopt some of the ideal assumptions from the symbolic model. In particular, we're going to model these cryptographic primitives something like this, where the ciphertext is going to be independent from the plaintext, except for some constraints. And so, for example, here we have constraints on the length that say that the length of the ciphertext is going to be dependent on the length of the plaintext. Furthermore, we are going to have probabilistic properties since we have probabilistic primitives, but because we're making some ideal assumptions, this simplifies our properties to essentially say, if an attacker observes a piece of information, can the attacker tell whether it came from A or it came from B? This ends up having a nice balance of capturing both fine-grained information and implementation details that consist of the trivial attacks that the symbolic model can miss. However, because we're taking some of the same ideal assumptions, this allows for both simpler properties, which then results in some better proof automation. And in particular, we've implemented this as an F-star library called Waldo. I'm going to switch gears real quick and talk about one of the key challenges to verifying protocols, and for us, that's non-determinism. We have to deal with non-determinism because the protocols we aim to verify are both concurrent and they are probabilistic. They do random sampling. The way we're going to handle non-determinism is we're going to try and get rid of it. First, we're going to take a protocol expressed in a probabilistic process calculus. We're then going to try and run a synchronization procedure to get, instead of this concurrent protocol, a synchronous probabilistic function. And I'll explain that in a minute. We're then going to factor out randomness essentially out of the program so we can just reason about a deterministic function. Well, this sounds kind of like magic, so I'm going to go ahead and talk about each of these components a little bit in turn. There's prior work that's shown that under some conditions, we can soundly reason about representative synchronizations of protocols rather than the concurrent versions of those protocols. And so this is prior work like Lipton's theory of movers, as well as canonical sequentialization. To give you just kind of an intuition for how this works, I have a simple protocol up here that has a client and a server. The client's going to send a message to the server and then wait to receive a response. The server is going to wait until it receives a message and then send the client a response. Because this is a simple protocol where the receives are going to be blocking, what we'll see is that there's only really one execution order this could go in. And so it is sound to just consider that execution order. There's some further simplifications we can do here, like since we're sending a message and then receiving it, you can essentially just replace this with an assignment statement. We can do the same thing for the rest of the program, and what we end up with is this much simpler synchronized program that's much easier to reason about than the original concurrent program. Notably, prior work has shown that you can do this whenever essentially the synchronization preserves the same outputs as the original protocol. However, in our setting, we need to consider probabilities. So it's not enough just to preserve the same outputs. We have to preserve the same outputs with the same probabilities. There's more information about how we do this in our paper, so please take a look. And I'm going to omit the rest of this in the interest of time. The second piece we want to deal with is once we have this synchronous probabilistic function, then we want to handle the randomness. Our key idea here is we're just going to replace non-deterministic sampling with a deterministic reading from a tape. Importantly, for this to be sound, the tape itself has to be randomly sampled from the same distribution that we'd be sampling the random numbers from anyway. So we're not getting rid of random sampling altogether. Instead, we're essentially just lifting it up into this tape construct so we can reason about the rest of the program as just a simplified function. What does it look like if we want to prove indistinguishability? Well, we can consider these two probabilistic functions, f and g. Formally, we can say that these two functions are going to be indistinguishable if the probabilities that they produce any particular value is equivalent for all particular values. Whenever we're dealing with tapes, what this boils down to is showing that for every tape, if we can show that there's an equally likely tape such that f evaluated on the original tape produces the same output as g evaluated on the new tape, then this property ends up holding. There's also some other restrictions like these tapes have to be drawn from the same distribution. But essentially, this is a technique called proof by coupling in probabilistic proving. This is also the same core technique that's used in probabilistic relational Hoare logic. And so proving indistinguishability for our protocols boils down to essentially having the user provide a bijection here that shows this mapping, much as a user may need to provide a loop invariant for program verification. I'm going to conclude real quick by talking about one case study we looked at. To give you a little bit of a background, we're going to talk about an extension to TLS. TLS is a protocol that's used to encrypt most of the traffic on the internet today. It starts off with this handshake process before deriving a key that can be used to encrypt further information. Importantly, the first messages are sent unencrypted in the clear. So TLS starts off with this client hello message, which contains within it typically the name of the server, or at least the domain the user is trying to connect to. The issue with this is if there's a sensor on the line, they now know that this is a connection they want to block. TLS encrypted client hello is an extension that aims to hide this kind of information. It does this by first encrypting the client hello, sending the client hello through a proxy, which is going to unwrap it. And then the rest of the handshake is going to proceed as before. The key idea here is if there's a sensor between the client and the proxy, they should not be able to tell what server a user is connecting to. And so this is what we're going to try and prove, is we're going to try and show that if there's a sensor that can take a look at this network trace here, they can't distinguish connections to different servers. Importantly, this was previously verified using a symbolic model, but as we mentioned earlier, there are trivial attacks that that symbolic model doesn't capture. In our model, we were able to prove this property, but we needed to add a few extra additional assumptions. Specifically, we had to make some assumptions on lengths, like that these interclient hellos have to be padded out to the same length. Otherwise, the trivial attack where an attacker can just take a look at the lengths of messages applies in this case as well. And the same thing needs to apply for messages that are sent back from the server, not just sent from the client. Importantly, there's also any fields that are sent in the clear, like the server hello here, need to be essentially identical across all servers. And so it's also important that these extensions are sent in the same order. And then finally, these finished messages need to be also padded out to the same length, or sometimes it's sufficient to just choose the same length hash algorithms. It's notable that these are all implementation details that are very easy to get wrong. So it's important that whenever we verify these kinds of protocols, that we verify them in these finer grained models that can capture these attacks. So it's very clear that these issues do exist. There's more I wish I could tell you about, but you'll just have to take the word of our spokesman here, Belly Mays, and check out our paper. There's some more information there about the synchronization rewrite rules we use for our synchronization procedure. There's a little bit of details on our implementation, as well as another case study on a private information retrieval scheme. And I just want to leave you with this closing thought. Whenever you want to verify privacy, just remember to ask, where's Waldo?
Right, great.
Thanks for a nice talk. How realistic is it in practice to do this message padding that is needed for the TLS protocol? Like, do you sort of need to pick the longest domain that exists and pad everything to that length?
Yeah. So it's not only the longest domain, but it's the longest. You essentially need to know how long can that encrypted client hello message be. And so there's partly the server name indication field. You need to know the length of that sort of, but you also need to know if those other extensions are there too, what could the longest response be across all the servers in the anonymity set. So in the spec, I kind of have this saying that that inter-client hello padding is adequately addressed, while the others is either inadequately addressed or missing. But it is there as an optional feature. So it'll be interesting to see what gets implemented. And TLS ECH, I believe, is being rolled out about now.
We have time for maybe one more quick question from the audience.
When you were showing how to get rid of the concurrency, you were saying things like, under some circumstances you can do this. Are these circumstances always fulfilled in the cryptography case?
Yeah, so it's not necessarily to do with the cryptography, but typically about how they communicate over the network. We argue that for a like reasonable set of practical programs, this is the case. So essentially, whenever these operations, so like Lipton's theory of movers applies whenever these operations can commute left and right. Process symmetry then applies to like broadcast cases and responses. And so we find that essentially for TLS DCH, because it has this kind of like very lockstep manner to the protocol, that falls nice and easily into kind of like this commutativity requirement, and then it's also over TCP, so we can kind of just assume everything's reliable. The process symmetry ends up being important for like the private information retrieval case, because those are all just like essentially broadcast calls out to end databases and then responses back. And so we claim that there's a non-trivial subset of protocols to which this applies. But if these conditions don't apply, we don't handle it.
All right, thanks.
All right, thank you. And that concludes the session.